So for Project 13, you were tasked with completing some recursive programs within a class called Euclid. So let's go ahead and get started. Our first method is called GCD, and it returns the integer greatest common divisor of two numbers, a and b. This method is going to be an implementation of the aforementioned Euclidean algorithm. So let's go ahead and write out the method signature. So GCD, int a and int b. The base case for GCD is to check and see if b already evenly divides a, at which point we can go ahead and return b. So we do a mod b is equivalent to 0, in which case we return b. The recursive case, we need to do the following. We have to implement the Euclidean algorithm that we just mentioned. So the Euclidean algorithm states that if we want to find the GCD of two numbers, that the GCD is actually equivalent to the GCD of the second number, or the lesser number in this case, and a mod the lesser number. So b comma a mod b. And this is eventually going to return to us the greatest common divisor of the two numbers. And there you have it. That is all there is to GCD. Next, we're going to calculate the approximate result of a geometric series of 1/2 raised to a certain power. This method takes one argument, and it's called geometric. So let's write that out. Double geometric. And what it takes as parameter is a single integer x that represents the exponent to which we raise 1/2 in a series. The base case for this is when we have 1, aka 1/2 to the 0th power. And that case occurs only when x is 0. So let's write that out. With the 0, aka that the exponent is 0, we can go ahead and just return 1. And then, if we, for instance, if we wanted to get the first, let's say, we wanted to go all the way up to 1/2 to the 10th power in the series, then we will have to do a little bit of recursion here. And the way that you can calculate each and every term of the series is as follows. You just have to return 1.0, and the reason I do 1.0 is because we want to avoid integer division. So we do 1.0 divided by, and we go to the math class for this, math.pow 2 to the x. We're going to add to it geometric of x minus 1 to account for all of the lesser, or I guess further to the left, elements of the series. And there you have it. That's going to be all of geometric. The next method is going to be used to compute the Basel series, famously solved and proven by Euler in the 1800s to converge to pi squared over 6. You can find this series in the handout, or you can look up more about it online. So the method works in a very similar way to the geometric series, but instead of using a exponent as the argument that we pass to it, we are going to use integer x as being the denominator of the series. So each of the series terms can be represented as 1 over x squared. So if we want to have the base case be when the term in the series is 1, what do we want x to be? Well, we want x to be equal to 1, because that would be 1 over 1 squared, which is nothing more than 1. Just like before, we're going to have a very similar recursive case where we calculate the other terms. So if we want to calculate one of the other terms, it's ultimately going to be reduced to 1 squared, aka 1, all over the denominator squared. And we could use math.pow for this, but really a simple way to do it is just to multiply x times x, and that gives you x squared. And then we add to that the prior term in the Basel series, x minus 1. And that'll do it for Basel. And then we move on to the final and arguably the most difficult method in all of Euclid, and that is called Scrambler. So it is going to take in a single string, string s, and it's going to absolutely make it completely unrecognizable. And what's really amazing about this method is that it can also unscramble the same word that you fed to it if you feed it to it once more. So if I feed in a word like dog into it and it scrambles it, I can feed it right back through and it'll give me the exact same result. For this particular method, we actually have 3 different base cases, so we need to go through them step by step. So for the very first base case, that is going to be when s.length is equivalent to 0. So we have an empty string. So let's go ahead and just return the empty string, because there's no real way to reverse an empty string, and there's not much scrambling to do. And then we have the second case, which is when s.length is equivalent to 1. And kind of similar to the 0th case, we can't really reverse a string of length 1. You can't really flip it from index 0 to index 0 and make anything significantly different happen. So we're just going to go ahead and return s in this case. Then for the third base case, we have if s.length is equivalent to 2. And for this one, it's really actually not that bad. We're going to have the initial string so that it knows that we're going to want to return a string. We're going to concatenate to that the second character, so we're going to use s.char at 1, as well as the first character. So we're going to use s.char at 0 for the 0th index. And finally, we have our recursive case. And this one is quite a doozy, so let's go step by step through this. First, we're going to return, and we're going to want to have the beginning part of the string be s.char at s.length minus 1. Because the very first thing that we're going to concatenate to the string is going to be the last character of the string. That's part of the scrambling. And then this wouldn't be a recursive step if there wasn't a recursive part of it. So next comes the recursive call from the second character up to and excluding the midpoint of the string. So let's break that down. We know that it's a recursive call, so we have to call scrambler. And we know that it's a substring of s, so we're going to do s.substring from the second character, which we know starts at index 1, all the way up to, but excluding the midpoint. And we know that that substring is inclusive for the first index and exclusive for the second index, which means that s.length over 2, or the midpoint index, is not going to be included in the string, which is just what we want. Then we have to add another recursive call from the midpoint all the way up to and excluding the last character. So now, just like before, we're going to have another call of scrambler on the substring, s.substring, from the midpoint. So we're going to start at the midpoint this time, up to but not including the last index. So we can do s.length minus 1, because we know that this is a exclusive second index. So it will not include the character that we already prepended at the beginning. And then finally, we just need to append s.char at 0, also known as the very first character in the whole word. And there you have it. That's all that there is to Scrambler. And so let's go ahead and run some different tests on this. So I'm going to go ahead and scroll down to a main that I created right here. So for the first thing, what we're doing is we're going to calculate the GCD of a couple numbers, and I've given the values over here to the right. Then we're going to see if the geometric series converges to what we think it should, which it should converge to 2 if my math was right. And then we're going to test Basel by doing up to 50 terms of Basel and seeing if it approaches 1.6449. And we should expect it to be a little bit less than that. Now, 1.6449 is an approximation of pi squared over 6, so we'll see what happens. And then for Scrambler, we have a cheer that we have here at Purdue. And what we're going to do initially is we're going to scramble it. So we take Go Purdue, scramble it, and then we print it out. And then we print out what happens when you pass that same cheer into Scrambler once more. And we should expect this kind of an output here at the bottom. So let's see exactly what happens. Awesome. So I'm going to go ahead and copy this over here so you guys can see the results a bit better. Shove it right here. There we go. So it looks like the first result we got was 2, which is good. That means that our GCD is working. The second result we got was 1, which again is great because those are both prime numbers and the only common divisor they have is really 1. And next, it looks like the geometric series, due to floating point approximation, actually got to be around 2.0, which is perfect. It meant that our geometric series was doing very well. And then Basel, it looks like it was, like we predicted, slightly less than 1.6449, but it appears to be approaching that number. So that's awesome. Scrambled string, so exclamation mark U Purdue, followed by Go Purdue, which tells us that our scrambler actually works both forward and backwards. So yeah, that's everything for this project. If you guys have any further questions, feel free to post them on the discussion boards. And yeah, that should be everything. I hope that you guys are more excited about recursion and that you guys continue to do so well in this course.